We have an exciting lecture today about capture of carbon. This is one of the seminars that we run in the Bolin Center seminar series that started in January 2017. So it's probably time to not repeat that this is a new seminar series. This time it's Research Area 3 that is hosting the event, and I will soon hand over to Magnus for the introduction of our speaker. And I'm very glad to have you here, Siggy. Thank you very much.
So, we have the honor to have Sigurdur Gislason from University of Iceland here today. He's working there from the Department of Geology, has been working in general geochemistry for a long time, and also been cooperating with some people at this department for a very long time as well. So, today Siggy will talk about the Achilles heel of carbon capture and storage. Research Area 3 thought it was quite important to have something about what can we do about CO2 increasing levels in the atmosphere on the long run. And that's why we wanted you to have a talk on this. Most research areas are working with effects of what's happening with CO2. It's increasing that will increase in temperature and so on. But I think it's going to be very interesting to hear this. So, Sigurdur.
Thank you very much.
I'll leave it up to you.
Thank you very much, and thank you very much for the opportunity to talk here today. I've had collaboration with people here for a long time. I think I've been working with Peter Thusander since 1977 or something like that, so we go a long time back. And also I'm very honored that I have a former PhD student here, Gabriela Stockman, and I will show some of her work later on in the talk. Now what I'm going to do here today, and I'm going to talk about the Achilles heel of carbon capture and storage. And the Achilles heel is twofold. It is safety and price. It is very costly to capture carbon and store it in the ground. And I'm going to show you some way to improve on that. But what is CarbFix? CarbFix is a international project that originally got started by Columbia University in New York, Reykjavik Energy, University of Iceland, and CNRS in Toulouse. And it was all about developing methods for storing carbon in rocks and industrial method, take it all the way to industrial scale. And at the present, we are actually there. We are capturing CO2 from a geothermal power plant and storing it in the rocks. But the second objective, and that was probably one of the most important one, was to create the human capital and expertise. So the thrust of the work was done by PhD students and postdocs. And so far 8 PhD students have finished, and one of them is here. And 3 master students have finished, and 2 of them projects are ongoing. And Sandra Snæbjørnsdóttir, she's going to defend 19th of April. So we've gone a long way, and if you want to find out more about this, we have a website for the project. Now, in the beginning, we of course wanted to go for field injection, and we had a field site, and where we started tracer test and monitoring of the monitoring wells. And at the same time, simultaneously, we started laboratory experiments, and that was mainly Gabi's work and a couple of others doing laboratory experiments, and then the hydrology of the system, and then these 2 were put into reactive transport models that were then used to simulate and predict what would happen when we injected. And also we want to know beforehand something what would happen when we injected, and then we looked at natural analogs and used some of the volcanoes in Iceland because they emit a lot of CO2, and we were looking at the reactions between CO2 from deep source with the rocks. So all of this. I will show you some parts of this before we inject it, and then results from the injection. And then finally, I will end with the industrial scale injection we are doing today. But before we start, I want to do a general kind of overview of why we want to do this. And then, of course, do a little bit of politics of carbon capture and storage and where we are today with respect to that. Now, this is a picture that you are all probably very familiar with. This is the CO2 concentration of the atmosphere, and this is going 8,000 years back in time, and this is going 100,000 years into the future. This is the air bubble record from the Antarctica, where we have high concentration of CO2 during the warm periods and the low concentration of CO2 during the ice age periods. And usually you see the scale of this really stretched out to kind of bring out the difference between the warm and cold period. And the difference between the warm and cold period is about 100 ppm in CO2. And we were here at the very beginning of the Industrial Revolution. Then we are here at about 280 ppm. Now this shows here some air bubble results, and then the monitoring that started beginning in Hawaii, and then we are here at the present with 400 ppm. Now what this shows here, this scary curve here shows what's going to happen if we take all fossil fuel on Earth and we burn it at the current rate, well actually not the current rate, at the rate increase that was 10 years ago. And if we would keep on burning it and do nothing about it, then just in 250 years we would reach this peak here, about somewhere between 1500 ppm and 2000 ppm. And then it will go down in the beginning because of dissolution in the ocean. Then we would dissolve all the carbonates in the ocean. And eventually the carbonates on land will dissolve and bring it down to here. And then weathering of silicates on land will bring it here. And it will take weathering of silicates about 500,000 years to 1 million years to bring it to pre-industrial concentration. So this is a huge, huge impact of the Earth. And you probably know all the consequences of this. Doubling of this to 560 here is a kind of general acceptance that will give us, on average, 3-degree warming. And then we will hit the runaway melting of the Greenland ice sheet and melting of the Antarctic ice sheets. They will give us this, and this, of course, will cause major political instability on Earth, and also acidification of the ocean. At the peak concentration here, we would have a pH change of 0.8, in the ocean. Now, the Paris Agreement from late November, early December, 2015, then we're aiming at 2 degrees or 1.5 degrees. So we're talking about shaving this up here. That is a huge, huge commitment to do that. And we have to keep it here to be, below the 2-degree scenario from the Paris Agreement. And if you analyze this, and this was already apparent in 2015, that the remaining emission to keep global average temperature to below 2 degrees, this is 900 gigaton of CO2, will be used up in around 20 years according to the emission pledges of the top 4 emitted to the COP21 in Paris 2015. And this is a sobering observation, a sobering fact. And if you look at this, this is a CO2 emission in gigatons of CO2 per year. And this is time here. And this is the year where we did the last scaling before the Paris meeting. And this is the sample pathway for about 66% chance that we are going to remain within 2 degrees. And this is the emission path we have to take. And then you look at what China pledged before the meeting. You look at what India did, EU did, and US did. And you can see it just by 2030, there is nothing left for the rest of the world. So the pledges, even though they look ambitious, it's not enough. And when you look at China and India here, you could point at them and say, well, this is unacceptable. You have to do more. Look like what we are doing. But if you take it into historical perspective and you look at the cumulative emission from the Industrial Revolution to the present, then you have this picture here. And you can see this is Europe from 1750 to 230. This is Europe. This is US. This is China. And this is India. So you can see it's a very complicated political issue to get this going. And I guess the part of the success with the Paris meeting was that the French diplomat, they kind of mapped out what was possible to get accepted. And for example, there was no price put on carbon. Because they said there was just no way we could reach an agreement on that. But so it is like a free, unlegally binding pledges, and we'll see what's going to happen. But at least for the last 3 years, the CO2 emission is not rising. It's not rising. It's been kept at more or less the same levels, 2014, 15, and 16. And we see what's going to happen in 17. Now, what can we do about this? Of course, we have to go renewable, wind energy, and especially here, well, actually in Denmark, I mean, it's spectacular what they've done, and also solar. And last year, China put their solar energy production last year was equal. The new solar energy that they produced last year is equal to all the geothermal energy that is harnessed on Earth. So China is really doing big steps. But the problem is there is plenty of fossil fuel, and it's cheap because there is no price on fixing carbon by burning the fossil fuel. There's a lot of it, and it will be used. So we have to do something about it. And this is what the International Energy Agency suggests that we do. And this is what is shown here in this picture is the cumulative CO2 reduction by sector and technology in the 2-degree scenario to 2050. So this is how much in total we have to kind of fix by CO2 or decrease the emission by CO2. And here is the scale here. This is gigaton CO2, and the scale here, 50 gigatons. I mean, last year's total emission from humans on Earth was about 40 gigatons. So you can see this is a huge amount that we have to the cumulative reduction. And if we look at the power sector, renewable, we really have to go renewable, and then more nuclear. And if we use fossil fuel, we have to capture the CO2 that comes from the coal-fired power plant, etc. And this is a huge task. This is more than 50 gigatons here that we need to capture in terms of, for example, coal-fired power plant, natural gas, or even oil. Now, if we even decided to leave completely all the fossil fuel left in the ground, and we were going to go then on just the renewable and nuclear, we would still have to capture CO2 because we will need our cement, we will need our iron, we will need our aluminum, and we have to capture the CO2 come from the production of that. And that is a pretty huge task. That's about 30 gigatons of carbon for capture and storage. So we need carbon capture and storage to keep within 2 or even 3 degrees C. Now, what is carbon capture and storage? And the most famous one is the Norwegian, or what the Statoil did, and started in 1996. They were harnessing natural gases here from this formation in the North Sea, but the natural gas contained too much CO2. So they had to clean out the CO2 before pumping it into the European market. They had 2 options: to just vent it off to the atmosphere and pay carbon tax. At that time, there was an offshore carbon tax in Norway, and the carbon tax was high. It was $50 per ton of CO2. So there was an incentive for Statoil to actually capture the CO2 and actually store it. So they separated the CO2, and then they put it into this Utsira formation, which is a sandstone and it's a huge formation, very permeable, mainly quartz sandstone. And then you compress the CO2 to liquid state, then you pump it down here because of the geothermal gradient. It becomes supercritical, but it's more buoyant than the fluids in the sedimentary formation, so it has a tendency to rise. So it rises up, and it rises up until it hits this shale layer here that we hope that will keep it physically down. The CO2 wants to come up, but we keep it down. And then over decades or even centuries, the supercritical CO2 dissolves into the water and then sinks down. That's the fingering, because as you dissolve the CO2 into the water, it becomes more dense, and then it sinks down. And this is one of the problems people are having with the acceptance of this. There's the danger of, if you have a rupture this cap rocks, that you will just get this big burp up to the surface of the Earth with some major problems. And this is one of the problem with this is one of the Achilles heels. People don't want to have this in the backyard and hoping there will be some layer caprock that's able to keep it underground. Earth has done this for millions of years. I mean, all our natural gases and oil is more or less from a caprock that was able to keep it down, within the ground for millions of years. And now if we look at what are these carbon capture and storage projects in the world and how much do we have? I mean, here in Europe, we have the Sleipnir area, and this is in Norway. Also, we have Snøhvit in Norway. And then this is time frame here, and this is up to 2020. And what's cooking in Europe? There is one Dutch project that's going, and UK decided to put these two on hold. So there is not much of an increase in Europe. I mean, Europe is completely failing, but the Norwegian government has put aside money for doing industrial capture. Most likely from a cement factory, but perhaps a smelter. And so there might be one here, Norwegian, coming aboard, and that's it for Europe. And you can see rest of the world, this one has been shut down, but there's this one is very interesting. This is an iron smelter in Abu Dhabi. And that's the first industrial capture in the world. This is Gorgon in Australia, which is going to be the last one when they put it online. And China there is activity in China and in the United States, but we don't know how the United States is going to fare for the next 4 years. This is 1 million here, the scale. And you can see if we take all of this together up to the year 2050, this is about 0.8 gigatons or 800 million tons of CO2 in total. According to the previous slide I show you, we need 80 gigaton or 80,000 million tons. So we're not doing 1% of what's needed. So we need a major increase in this area if we're going to get below the 2 degrees, thing. And this is the second Achilles heel of carbon capture and storage. It's so costly. It costs so much money. And the main cost is from the capture process here, where you have to separate the gas and you have to compress it into a liquid-like state, and then you transport it. This is where the most possibility is to cutting the cost. This is the transport cost. Injection is relatively cheap, and no one talks about the monitoring cost. And this is where we really have to work down the price to get something going there. And this is Europe's, total failure. This is the cornerstone of European environmental policy. This is the Emission Trading scheme. When it started here in 2006, the price of this, the idea was that you could either buy the right to emit, or even you could sell it. If you were capturing and storing, or even if you have negative emission, you could sell it on the market. This worked well for the SO2 emission in the late 70s and early 80s. And so here it was put on the market, and you could see the price for it was from 20 to 25. Then it kind of went through the roof, through the bottom here. And then you have seen this fluctuation. And what happened is there was too many quotas set on the market, plus some of the heavy industry was outsourced to India and China. There's too much quota around, and so the prices have been dropping, and then there was some political measure to try to increase the price, and you could see leading up to the Paris meeting, it was rising up towards 10, and then when there was no legally binding solutions for the power companies and industrial companies, the price went down here, and it's been sitting on €5 per ton of emission, and you can see the cost of simply capturing. Well, actually, we can probably capture for less than this, but you can see there is no incentive for the companies to do anything. I've been trying to approach aluminum smelter and so forth, because every year they can just emit without paying more than €5. They say, well, we make a lot of money not doing anything. So this is stalemate in the environmental policy of Europe. And this is one of the reasons nothing is happening there. Now, what do we do, in Carbfix to attack this? We're trying to do both. We're trying to attack the safety and also the price. We're trying to do cheaper, capturing, and we are trying to do more safe thing. This is our caprock that is really holding it down. So what we do, we take gas from a power plant. In the first step, we took pure CO2, and we put it, and this is at 30 or 35 bar pressure, and we put it into our well, injection well, at about 250, or if we're doing a 35 bars, 350 meters depth. And it's just like in your fish tank, we try to form as small bubbles as possible, but because the buoyancy force is really dependent on the radius. Of course, the density difference, but it's mainly the radii. And the smaller the bubbles, the less the buoyancy force to bring it, because the bubbles want to go up here. And then you need a critical flow velocity around the bubbles to overwhelm the buoyancy force and actually start to bring it down. Once they start to descend, then the beauty of it, the bubble shrinks like a balloon as it goes to deeper, higher and higher pressure. And that keeps on the diffusive force through the bubble wall. So when we were doing this, we had video cameras down here. Even when we did some experiments in the stairwells in the Manhattan skyscraper, having like tubing down and then video cameras to study this. And in the end, it takes about 5 minutes here before everything is dissolved. And then we're home free. We've killed the buoyancy force. This is more dense fluid, and it's actually pretty dense. I mean, if we go to the Henry's law solubility at 25 bars, this is 1 molar, solution. It's 1/10 of a concentrated hydrochloric acid, for example. So it's dense, and the pH is low. It's 3.5. So it is corrosive, and it attacks the rocks. And it's very important in the beginning that it attacks the rocks because it creates porosity close to the injection well. We don't want it to precipitate right away. So here it creates porosity. And then as it goes further and further away, pH rises because of the reactions with the rocks. And eventually we reach supersaturation with respect to carbonate minerals, and they start to precipitate out. And then we're home free. It's rock stable. That's the phrase we're using for it. It's rock stable, and it's the safest way of storing carbon in the ground. And why do we want to use basaltic rocks? Because they look like dense rocks and are not very impressive to put in. There's not enough pore space, etc. And it's very important that we dissolve here and then we precipitate in the more distributed system. And the reactions, these are the reactions where you have simply, and you can do this in your, some of you do this with your soda stream at your home when you create your, you have CO2 going to carbonic acid, and then it dissociates the bicarbonate and H+. So this is what creates the acid. But the beauty of it, when you dissolve the rocks, you consume the protons. So you neutralize it. Basaltic rocks is a basic rock. It acts like a base, and it neutralizes the acid. It consumes the protons here, and then you get these ions into solution. And then when you have the pH has risen enough, then the activity of this species gets high enough so you can actually reach supersaturation and you form carbonates. And we know that at the lower pH we form citrate, the iron magnesium, at the intermediate iron magnesium and calcium magnesium, and at the highest pH we form the calcite. So this is like a sequence of one carbonate taken after another. And so this is an important, and also for if we want to cut down the capture cost and put dirty gases down there, for example, H2S or even SO2 or even NOxes, you have the same kind of reactions. You create some acid as you dissolve, and then the basaltic rock will neutralize it, and that will release the cations that can then hook up with the gases and form, at least in terms of H2S, SO2, and CO2, it will form some minerals down there. And you can cast these aqueous differently. This is glass. If it are minerals, you can see that you have the same thing here. You consume and consume and consume the protons, release these guys, and to precipitate these. And actually, if you cast it in terms of CO2 here, when you precipitate, you actually start to acidify. And so it's all about the dissolution drives the pH down coming from this, and also the protons coming from precipitation. And so it's basically the basaltic rocks acting as a base in the whole system. So before we injected, it was very important to study the kinetics of this, how fast this would happen. Because what had been predicted before, for example, for sedimentary basin to form minerals in the sedimentary basin, it would take decades, centuries, or even thousands of years to do that. So, and we knew from the beginning that this would be the rate determining steps because carbonates, they precipitate very rapidly. So we performed several experiments before we injected, and this is an experiment done in Toulouse on the phosphorus dissolution, and this is moles per square centimeter of the surface area per second. This is pH here, and you can see olivine dissolves very rapidly at low pH, and then as the pH rises, it kind of slows down and down. And the pyroxenes do a little bit similar, have a similar pattern, but they dissolve pretty slower. And then the basaltic glass dissolves very rapidly at low pH, then it decreases rapidly and much, and then the dissolution is lower. And then when we get to high pH, then the basaltic glass dissolves actually faster than the olivine. Similar with plagioclases. You have the same, there's some famous experiments from this department, on the dissolution of plagioclases. And so it looks from this that at low pH, and this is the pH of our injected fluid in the beginning, that, for example, if we have a fracture going through basalts, it will be the olivine and pyroxene. It will primarily be feeding in the cations. As we get to higher pH, it will be, then the plagioclase would take over. But if we're mainly water is flowing along the bottom and top of the lava flows, because they are glassy. The top of the lava flows and the bottom of the lava flows are glassy, and then we're mainly dealing with basaltic glass, just as is happening on also the oceanic ridges. Now this is the dissolution rate, and then simply for looking at this for basaltic glasses, we can see with pH that the relative release of calcium over magnesium and iron, we can see at the low pH, there is mainly magnesium and iron being released here, but then in the high pH end, it's calcium. So this is one of the reasons why we are getting siderite and magnesium, iron carbonates in the beginning at low pH when we start to precipitate, but in the end, we always end with calcite at the low partial pressure of CO2. Now this can be modeled, and this is just a simple reaction path modeling for a batch reactor like this. And we start with let's say we start with our groundwater, and then we put 2 bar CO2 pressure on it, and this is mineral fraction formed, and here is in the beginning you have a little bit of mixed clays at this low pressure, and then carbonates, and then as the pH, as time goes down, we form zeolite, mixed clays, and carbonate. If we jack up the pressure, you can see the efficiency of the system increases. We get relatively more carbonates, less clays and zeolites, and at the highest pressure is mostly carbonates, a little bit mixed clays, SO2, and some silica aluminum minerals. So it seemed to be, we want to do this at a relatively high partial pressure, CO2 high pressure, to make most use of the released cations, because any calcium, magnesium, and iron put into clays or zeolites, they will consume the pore space. And rather than pore space for the carbonates, we will have aluminum silicates there. So it's all about how efficiently running your system. And then the final step we did before injection, and this was part of Edda Aradóttir PhD study, and she did this in collaboration with Lawrence Berkeley Laboratory, who also developed a tough react model that can simulate both the hydraulic flow and the reactions, taking all these rate equations into account. And this is actually cross-section. This is our injection well, and these are our monitoring wells. And this is the concentration mineralized, that's the models, calcite in terms of the volume. And this is, the plume is moving from here to here with time. And she predicted 85% of the injected would be mineralized in 5 years. And in 10 years, everything was mineralized. That's what she predicted. She had major problem pushing this through publication, because everyone said, this is going to take decades or even thousands of years. This is ridiculous. But she got it through. And then the next step, of course, you can model, I forgot your work, Gab. Another thing that we were so afraid of, when we have the surface of the rocks, where we're going to get all our calcium, magnesium, and iron, but then when you start to form the carbonate, that you would pacify the surface. You would just shut everything off. You wouldn't get any calcium, magnesium out, and you would form some carbonates in the beginning, and then nothing would happen. And we were very excited, and Gabi did several of these, and we were, she would run an experiment at pH 10, 25 degrees C, experiments when she was measuring the dissolution rate of basaltic glass without any carbonates forming, and that is the control, and that is this one here. And then she did experiments with the exact same material, with a lot of carbon precipitating on it. And there is within the experimental error, there's no difference. So it looks like that the cations are able to kind of migrate through the carbonate. So this was also very encouraging. But you never know until you do it. So we decided to go ahead and start to inject. And this shows the gas and tracers going in, and these are 3 generations of PhD students. This Santa is depending now 19th of April. She's the last one in there. Gas and tracer going in here, water and tracer going in here, and here we put the video cameras and high pressure samplers. And this is our experimental site. This is the heavy-sided power plant here. These are roads and the surface properties here. Actually, this is air photos showing the post-glacial lava flows. And this is our injection well. I showed you a picture from the top going 2,000 meters down. And we took water from the same formation actually upstream here. And the pH of this water is very high. It's pH 9 to 10 because of all these protons being consumed during the reactions, because basalt is a base. And then we took the CO2 here from the power plant. In the beginning, pure CO2, and then later on, 73 of this gas mixture. And this is very important. We put tracers, with our gases, and these are conservative volatile tracers like SF5 and later on SF6, and then later on SF5 with the gas mixture. And also, we were allowed to label our carbon with carbon-14, so we could really trace the flow of this. And then we produced out of this monitoring well, about 2 kilos per second, and this was 1 kilo per second injection, because we want to pull the fluid towards us, because we had PhD students working on this, and they want to finish in 3 to 5 years. So we can't wait forever. And so we're pulling the fluid towards us, and the temperature there is 20 to 50 degrees C, and the distance, this is a little bit more than a soccer field, just straight across here, but some of the fluid goes here and then through a fracture, and this is about 3% of the mass, but some of the fluid goes deeper down and more tortuous path, and then it makes it to the well. And now I'm going to show you data from the monitoring well. And this is our tracer here, the SF5 that went with the pure CO2. And this is time. This is the first injection, then the second injection, and this is monitoring time. I show you here the first 550 days after the injection. At the end there, it ended here because our pump broke down, and I will tell you a story about the pump in a minute, why it broke down. First, we get the tracer here in the beginning, a fast breakthrough, about 3% of the mass goes through here, and then the concentration decreases, and then it goes up again, and this is the tracer just with the pure CO2 injection here, and it goes up and up and up, and then it reaches a peak, and then it kind of goes down here. So we have the peak of the kind of more pervasive flow here coming through about 450 days, after the injection. Same thing with the second injection, where we have the SF6 here, we have a peak, and then it's still rising when the pump broke down. Now here's the pH, and this was the exciting thing. We start with the high pH because basalt is a base, and then we see the plume coming in, and then the pH goes down, down, down here. And here we were kind of scared. This is going to be a major embarrassment. We're going to just end up having pH, 3.7 and nothing happening. And then it kind of turned up again, and the pH rose. And then we injected the gas mixture. It went down again and up, and then it rose. It took a little bit of excursion down at the peak of the pure peak going through, and then it came through here. And also the dissolved inorganic carbon, you can see it's a mirror image of this. The concentration increases, goes down, increases, and it did not go up, actually, where it should have gone up here. And then it kind of dies. Now we can do a mass balance, because these are inner tracers. We can account for the mixing and dilution because of that, and see, we can calculate how much thick dissolved inorganic carbon we should have seen if there were no mineral precipitation. And we can use the tracer for doing this. And that's shown here. This is the calculated thick concentration that is shown here. This is the observed. The difference is the consumption of CO2 by carbonate precipitation. And we showed here, we're able to show here that in about 400 days, 98% of it was consumed by precipitating carbonates. And we can do the similar mass balance on the carbon-14, and about 95% of it here at this peak value was consumed by dissolving carbonates. So this was pretty amazing results. And it kind of grows on you. In the beginning, when we're just looking at the monitoring data, one pointer after, there's nothing exciting happening here. No, it took us about, hey, it's because we're mineralizing. And then you have it, and then, we have similar concentration pattern for various elements. I'm not going to have time to show you in too much details how this is going. And this is the saturation state. We can take the chemical analysis, we can run it on various models to look for the saturation state, and you can see in the beginning, this is calcite, and calcite is in the rocks before we inject, and then it gets very supersaturated, and then it becomes undersaturated. We're actually dissolving probably some of the secondary minerals in the rock, but citrate becomes, the iron carbonate becomes supersaturated, then calcite comes again, we re-inject the gas mixtures, so forth, and then in the very end it's just calcite, but in between here, citrate and the magnesium carbonates are soluble. And when we brought the pump up, we analyzed it, and it's all calcite. We're just too good at mineralizing. We're just killing the pumps. And so this is how we changed. This is a very famous picture from the IPCC report on carbon capture and storage that was published in 2005. And this picture has been attributed to Sally Benson at Stanford, where you see the trapping contribution. This is a structural trapping I was talking about in the beginning. When you have a layer that physically has to hold it down, then you have residual trapping. This is similar to when you have a sponge in your bathtub. That is the capillary trapping. Eventually, you have the solubility trapping, where and for the sedimentary basin, this is very important, because this is when you dissolve it in water, and then you get the fingering down of the CO2. When you kill the buoyancy force. And then finally, you have mineral trapping, 100 years, 1,000 years, or 10,000 years. We do solubility trapping in 5 minutes. That's when we dissolve it in the well. And mineral trapping in 2 or 3 years. So it's a completely different picture for if you inject it into reactive rocks, then, you're talking about completely different scale. But this time scale is probably still valid for sedimentary basin, because here it's mostly quartz. There's no source for calcium, magnesium, and iron that actually provide the ions for the minerals that are there. And now in the final minutes, I'm going to talk about the industrial scale. So basically what we did with this Carbfix thing, I think we've learned a lot. And there are strings of paper still coming out of it, and we're understanding and modeling the observations now. And also what is going to come over the next couple of years is that we always took samples for several of these new isotopes. We're looking for new tools to prove in a cheap way that you're mineralized. So we've done calcium, magnesium, iron, lithium, you name it, isotopes in this. And that's work both with PhD students and collaborators at Durham and Oxford and University College and also in Toulouse, France. But Reykjavik Energy, and this is the new project now where we're putting industrial element into this, and now I'm going to discuss a little bit the money issue of this, how you can cut down the carbon capture cost, mainly in the capture cost, by taking impure CO2. And Reykjavik Energy is actually injecting 25 million tons of geothermal brine into the system every year, because they can't dry up the system. They have to use the water to bring up the heat from the earth. So they are injecting. You could put some CO2 into that stream. And actually, theoretically, we could put 1 million tons of CO2 every year into that stream. Because if you run this at 25 bars, there's about 25 tons of water to each ton of CO2. But Reykjavik Energy doesn't have that much of a gas, for us. But there's a lot of potential there. And this is also done when you're pumping up oil. This incredible injection of brine, and also brine to push out the last part of the oil within oil fields, and also pure CO2 is injected to push out oil for more consumption. So this is this is Deirdre Clark, the last PhD student in the project, and she is doing this high pH end. And what we're doing, rather than dissolving within our injection well, we're taking CO2 and H2S that dissolved in condensation water in a scrubbing tower by the power plant, and then we're injecting it into the hot part of the system, and we're forming carbonate and sulfides, and conservative tracer arrives month months after the injection. We're talking about now, not years, we're just talking about months. But there, we know at this high temperature, reactions are much faster. Also, there is no bacteria down here, and so it's a sterile system. So it's a little bit more easy to understand it and control it compared to when you do low temperature systems like 20 to 50 degrees C. And this is the scrubbing tower. I'm not going to go through the reactions, but basically we have ingoing gas and outgoing gas charged water with pH 4, 20 degrees and pressurized to 80 bars before injection. And we put in tracers. You know, we're using the new tracers, but similar methods as we used in CARFIX 1 to actually account for this. And we can see that, you know, here's again the hydrogen sulfide. This is the calculated concentration we should absorb. This is what is absorbed. The difference between here is what is mineralized. And we are mineralized here now in months because this is much higher temperature. And this is important because you don't want it to get all the way to the production area. You know, you want to mineralize it rapidly, but not too fast. You don't want to mineralize it right close to your injection well, because then you clog up all the flow paths. And the same thing for CO2, you know, difference gives you the mineralization of it. And this is my final, well, I'm getting too close to the end of the talk. This is the 4 steps in carbon capture and storage. This is the capture, transport, injection, and monitoring. And these are the numbers I showed you earlier, which are numbers from 2011. But I think we are, you know, maybe at Utsira we're getting down to 30 to 40, US dollars per ton, you know, in the capture cost. We are able to do this at the Reykjavik Energy sites for 21, US dollar per ton. So we're getting towards the area where, I mean, if we had a proper carbon tax in Europe, that this is doable. And it's doable, the reason for why this is cheaper than here we can take a gas mixture. Here we're investing a lot of energy and absorbent, like amine absorbents, is just to get a pure, dry CO2. And that's the difference. The transport, I mean, in our case, the transport is more expensive because we transport water with it. But if we are at the site where we have basalt, then it's good. Injection is more costly in our case, but if you're injecting anyway, then there is very little added cost. So, because I mean, Reykjavik Energy was injecting water anyway, so there's a very little added cost if you're injecting water there. And monitoring cost, there is some monitoring cost, but much less if you have minerals down there. But if you have a supercritical gas that wants to get back up to the surface, there's much less worry. And also what's interesting, and this is what I'm trying to sell the companies, Reykjavik Energy is forced to fix their, oh, Peter, very nice to see you. I'm just at the end of my talk. If you're going to fix, you want to come through? If you're going to fix H2S, Reykjavik Energy has to fix H2S. If they would take a conventional methods and just take it from the shelf and use amines to do this, the conventional cost for this is $300 per ton. And so we can actually save them money for doing this. And the same thing, I mean, if we are approaching a coal-fired power plant, you know, they have to fix their XO2. And this is one way of selling this idea to the industry and the power industry and so forth. Now, where can we do this? Where do we have basalts on the continents? Not much in Sweden. We have about 5% of the continents is covered with basalts. And there is an experiment that was published that the Pacific Northwest Laboratory was doing here in the Colorado River basalts. And they have the same results there. They injected supercritical in the basalt, but still, you know, they are mineralizing in 2 years' time. And now we are involved with a pre-project. Department of Energy has put funds into 10 projects in the US where they're going to do preliminary studies of where to do this. The idea is to take CO2 from Canada, pump it across here, and inject it in the oceanic ridge north of Vancouver Island. And that's what we're working on now, and we see if it gets a big fund. The Saudis are very interested in what we're doing, and they spent half a week right before Christmas, because they have about size of Iceland here in terms of basalts, and these basalts come nearly all the way down to Jeddah, and there's a huge CO2 source there. And they are thinking of either using sewage water that has gone through first cleaning step, and then inject, or possibly they could also use seawater. It's actually very interesting in using sewage water because the carbonates, they clean the water. If you take water that is not fit for human consumption because of, let's say, some heavy metals and so forth, the carbonates are precipitated out. They clean out, they scavenge the metals. And actually what you get out of our monitoring wells, you can drink the water according to standards. So this might be one way of actually using the water that is not fit for human consumption. But this is actually the Achilles heel of carp-fish. We need a lot of water. If we run this at 25 bars, you need 25 tons of water to each ton of CO2. So you have to do this in the coastal areas. And of course, if you need a lot of water, you can just go to the ocean. Of course, the bottom of the ocean is all basalts, well, most of it. And so you could, and the beauty of carp-fish, you can inject into fractured rock because the density of your fluid is less than the surrounding formation. And Sandra Snæbjörnsdóttir has actually, just for the fun of it, calculated the storage potential of the oceanic ridges. You could take all the CO2 stemming from burning of all fossil fuel on Earth and you could put it all into the oceanic ridges. But how much of it is of practical importance, we don't know. So what I've done, first I've given you a bleak picture of what the political situation is, in terms of carbon capture and storage. We really need to somehow get around this bloody, well, excuse my language, the emission trading scheme in Europe. And we have to bring the cost somehow down or just directly put the price on carbon, and then we get the industry on board because the industry is very hesitant. I think I've shown you, I'm not going to be humble, a very elegant way to the solution. It's not going to be a silver bullet. It's not going to solve our problems, but it's something that can be used in parallel with conventional capture and storage. Most of the know-how and knowledge is actually residing within the power companies like Statoil and others. And they've been doing this since 1996. That's where the thrust of this will be done. But carp-fish can be used along with, especially if we have the polluting source close to basalts. And I mean, that's something to think about in the future. We should store our power plant, if they're using fossil fuel, in where the formations are. We should transport then the electricity, but not the CO2, because that's cheaper to transport electricity than CO2. And finally, I think we've learned a lot in the process, and we've trained young scientists, both in doing fundamental science and some applied science, and I think that's a happy marriage. Thank you very much for your attention.
Thank you, Siggy. Does someone have a question? Paul? Oh, Nina?
One question. You say that it depends on political will, of course.
Mm-hmm.
You said that it depends a lot on the political will, of course, and you've shown us what you did in the project and that you try to get the industry on board, but you need to communicate this to the stakeholders, right? How do you do that?
I think we've actually communicated a lot. Last summer when the science paper came out, we were in the press everywhere, and actually we did 2 rounds. You could see it, we went with the sun, we got 2 rounds in the press, actually the headlines in most major. So we can't complain. It was mostly about scientific findings, but since then, we have really got the attention and tried to convey this to the political decision makers, but it's hard to get their attention. Actually, the beauty of it, we have Reykjavik, backup of Reykjavik Energy. I mean, and this is one of the largest geothermal companies in the world. And so, but it's still a small, now what we're taking about 16,000 tons per year. It's a small thing compared to the gigatons that we have to take. But it's very important that we have developed a technology. It's very simple to scale it up. I've had some meetings with I had a meeting one morning with representatives from all the aluminum smelters in Iceland because they are the main emitters. And I couldn't get anywhere with them. They just want to see what happened, Will there be a direct price of carbon or not? I'm kind of surprised also, I don't know if you are aware of this or about this double system. We're all talking about our commitments for the Paris meeting, and I think Sweden is doing quite well. It looks like you're gonna be doing quite well, because it's just about all the companies that are emit less than 100,000 tons per year. They are under the umbrella of Sweden. Same thing with Iceland under the umbrella. The heavy emitters, they are under Europe, and they are in the emission trading scheme. And that seemed to be a complete failure. And this, I think the media has not got it. And this is something that we have to communicate to the media. And you could see in terms of carbon capture and storage, it is one project in Holland, and then I guess Norway, I mean, of course they're doing beautifully, but I think it's because of the bad conscience about all the money they got from oil. And of course there's someone else is burning the oil that they're pumping up. And UK has decided to go nuclear rather than, start these two big projects. So it is, now it's a big step. I mean, how do we communicate with the politicians? How do we get attention of the media? I spend a lot of time with it, but I'm going to try to spend more time with my science, in the future. But I give talks like this, an interview. We have, after the science paper last year, we probably still have people like BBC and Al Jazeera coming in, or maybe once a month. So we are still, we're still getting that attention, but not the headlines.
So Siggy, yeah, this is very interesting. But if I understand you correctly, this capture is only, say, for heavy industry or heavy emitters like hydrothermal industry, oil industry, or coal burning or so. What is the, say, cutoff to the? You can't do carbon storage of atmosphere. The CO2 that's already in the atmosphere, as I understand. No. I mean, Klaus Lackner was actually with us in the beginning. One of the idea was to put. I don't know if you know it, Klaus Lackner is trying to produce these artificial trees, and he claims that he has solved the energy balance, that you can actually compete with trees, because what he and Wally Brooker are saying, it's not enough to capture from concentrated source. About 40% of the total emission to the atmosphere is from concentrated source. That can be captured and stored, just what I've been describing to you. But 60% is from ships, planes, cars, etc., and we can't put our Carfix thing, in the back of a car or a plane. But actually, Klaus Lackner toyed with the idea of putting some olivines in the keels of big shippers, and then have some, take the CO2 and then you actually pass it through a reactor, and then you just put it in the keel water, and then you create enough alkalinity, lower the partial pressure. It's not going to go to the atmosphere, but he's a free thinker, but Klaus's company is bankrupt now, but he is, I think this is a map, let me see, where do we go in the Southern Ocean here? Is Kenguland Island here? Where is it? Here's Element, where is it? This is the most windy island on Earth,
And he's going to put up his artificial tree there, because there he has enough wind to solve the energy balance. We'll see how it goes. But it's, no, I mean, what do we do with the planes and so forth? But still, if we took everything from the concentrated source, that will, that might, yeah, take 40%. That might do it. And that is doable. That is, we have the technology, but the technology is expensive. And there's more than enough storage space. The problem is, I mean, and most of it will probably done offshore. You know, if you move a little bit away from here, I mean, I was in a project called Nordics, and we were fantasizing about, you know, hubs collecting. You know, there is some storage space here. You know, Denmark has some of it, but most of it resides within Norway here. And we were fantasizing about all pipes, you know, going all the way here if we were going to take it from all these companies. You know, in the beginning you start with ships, but then if you have lots of transport, you have to go to pipes. And but it has to be, I mean, we are running out of time. I mean, we have to, you know, when you see this, and also Gabi yesterday at dinner was telling, you know, she's been interviewing scientists about the runaway melting now in the glacier ice sheets. I think we're desperately, you know, running out of time in terms of doing some of this. And Europe is a major embarrassment. I hope maybe China will help us, because also they're so desperate because of their SO2 emission and the particle pollution. And for them, it would be very appealing to take, you know, from the coal-fired power plant, both SO2 and CO2, take a dirty CO2 and use something similar to what we're developing. They have some basalts, but I mean, I think there's a huge potential in India. I mean, here on the west coast, using seawater. You know, there's a huge, and they, you know, they're building coal-fired power plants so rapidly, and they should, you know, start to get this going. I spent sabbatical in Australia, in Melbourne last year, and they are actually, there's a lot of money, you know, for this between China, India, and Australia. And they were thinking of starting a project in India, and they had a carbon source, but they had not made up their mind whether they're going to go carb fix or just a simple supercritical injection into basalts. So there is some movement, but it's very slow and way too slow. And especially for you young people in here, you know, it's a bleak future, but what is important, I've been trying to activate, also talking about communicating, you know, artists, and because we've failed so incredibly in communicating this to the general public. And just if you read the IPCC report, just the names, for example, of the emission schemes, it is ICD13, BCX6. It should be, you know, Gabi or Siggi or you know, Per. You know, have names so we get able to communicate with it. It looks like a conspiracy, and perhaps it is a conspiracy. Just, you know, if you read the abstract, you know, for policymakers, read it. You know, it's not a pleasure reading. You know, it is incredible. I mean, we have to somehow, you know, communicate. And I think the solution is we have to get the artist on board to communicate with the people. And I don't know if you've seen a movie by, what's his name again, the actor. Yeah, DiCaprio. I mean, I got a lot of response from young scientists all over the world saying, you know, what can we do, you know, after they saw the movie? At least, you know, it kind of, well, it's a little bit similar to what we saw from Al Gore in 2006 when he put out his movie. Of course, it was a little bit repetition, but it's I think we need to communicate. We need to communicate with the general public. Did you have more questions, Per? It was a little bit of digression from your question.
No, okay. Other
Siggy, I was just remembering in the beginning there were some test sites in Europe, like in Germany.
Yeah.
Ketzin, I think it was
called.
And then suddenly everything stopped, and I think both Denmark and Germany, they actually banned.
Yeah. This is actually a very important point you're raising. After Ketzin, you know, they were, I don't know how much they injected, I think about maybe 100,000 tons or something like that. And then there was a lot of hearings afterwards. And, during these hearings, the scientists would ask, well, are you 100% sure it's going to stay down there? And you have to give them an honest answer. We are not 100% sure. And then we're not going to allow it on land. And the same thing with, same thing with Denmark. They decided they were not going to allow it on land, but offshore. And so therefore, I think most of the storage that we're going to do, because when we do this supercritical storage, with the buoyant gas down there, it's going to be offshore because of public acceptance. So that's going to even add a little bit more cost to it. Of course, if you, for example, if you fly over Germany or UK, you can see, it's so heavily populated to anything like Iceland that, it's, no one wants it in their backyard. But there are huge gas storage formations that are actually used. We pump natural gases actually into just geological formation just for storage, and then we pump it out in several places in Europe. I think there is one actually very close to Berlin when they have this. And then there was, I think, wasn't it in California when they have a leakage from one of these storage sites, methane leaking, and they haven't been able to stop the methane leaking. And you can just imagine what that does for public acceptance. So it's going to probably be mostly offshore. And there's Norway is sitting very nicely. They have huge sedimentary formation. And just the Utsira formation out here that I showed you earlier, I think they could take most of the emission, from concentrated source in Europe there for decades. So, there was so much development in this when we started Carfix, and well, I hired you in 2007, and we were in the startup phase, 2006 to 2007. But the Norwegian, what do you call it, Geological Survey, or it's a royal something, they put out a bids to the open market to buy pore space within the sedimentary formations where they had good cap rocks. Because they could see this just as oil was a commodity, but pore space, where you can store CO2, and actually there was some movement in the beginning. But then when we couldn't put a price on carbon, then it kind of all died. But you can see if we had a price on carbon, let's say it was 30 euros per ton, there's a business in this. And then there comes the business to develop more economical way of smelting metals, for example. And my dealing with the aluminum industry, they always say, well, it's such a dilute stream. It's less than 4%, maybe between 2 and 4. It's so expensive to dissolve it or compress it. You have to jack up the pressure so much, and it's going to cost so much energy just to pressurize it. What they don't tell you is that in the beginning, when you smelt aluminum, you start with 99% CO2, and the rest of it is fluorine and SO2. They leave then the smelters open, and then they soak in air from the house around the smelters, just to make sure it's clean, for the people that are working in there. They could find a different solution for that. They could start with 99% CO2. That would be actually relatively simple. And this will be the future. This will be done in the future. And if we had price on carbon, all the smelters would be moving in the direction of doing this and developing these methods. But there is not an incentive for them to do it. And that's a terrible thing. Just throw it to him.
So how do you get the quota system up to? If even the starting price was $25, you would still have to double that price to $55, or let's say about $75. What are the possibilities to have that quota system up there?
Let me see. Now I'm not an expert. Let me see. This is not my computer, so let me see. I'm trying to get it into a. No, this is. I want this guy. Okay. I don't know. The honest answer is I don't know. I think these rises are due to some political movement in Strasbourg when they were trying to cut down the price. I saw educational TV, I think it was on a Danish TV, and they were interviewing Connie Hedegaard, the former Danish environmental minister for the environment in the former EU government. And what they showed in the program also, the mafia is in on this, and is actually buying, and you know, they find a way how to make money on this. So I don't know. It is just an utter failure. How can we fix it? I think it goes something like this. In the beginning here, for example, I think the aluminum smelters got 75% of their emission free. Every year, it was going to go down by 2%. You know, the idea was that there would be less and less, you know, free emission, and in the end, after several years, they would be pay for everything that they were emitting, and at the same time, the price should go up and up and up and up. And you can see what the record is. And this should be discussed at every parliament now in all of the EU countries. And it should be discussed in EU. But it's not. I don't know why.
Isn't the price a function of how many quotas and how much you can actually trade? I mean, there seems to be an overabundance of shares that you can trade.
There's no question about that. There's overabundance, and I think some of it was that, of course, there were lobbyists trying, you know, we're going to need more quota and so forth. But I think some of the heavy industry was outsourced to India and China. You know, I think, for example, aluminum, I don't know how many aluminum smelters have been built in Europe over the last decades. I know a lot was built in China. There was 2 in Iceland. You know, I guess we'd always a little bit behind. At least there we could do it. Now, so there's that. But you know, of course, I mean, we're discussing a lot now the politics. But don't forget, we created some really beautiful fundamental science on the way to solve it. And I think this is, I think what I like about this, although of course this is well, it's not just mine. This is our project. And we had a very nice mixture of like what Gab was doing and Snorri and the people are doing the experiments. These were fundamental research that can be used to any natural processes or applied processes like this. There's lot of it was a lot of fun to work with engineers and even plumbers. You know, we have very good plumbers. You need good plumbers to do something like this. And now when I'm interviewing new PhD students, and I ask them, have you done any plumbing? Because you think about it, experiments in the lab, it's a lot of plumbing thing. And so a lot of very elegant, you know, engineering solutions. And also we were able to get a lot of research money to do something we would not have been able to do otherwise. And we have very good and well-equipped labs here, both in Iceland and also in Toulouse, you know, thanks to this. And there's a lot. I mean, I feel there's more interest even in the US than in Europe for what we're doing. Maybe it is because there is not enough. More or less, the carbon capture and storage money that is given is to these big company and big innovation centers. We've been trying to sneak in between there. But a lot of the money we got is through Marie Curie networks. I guess you were a Marie Curie, or you were not a Marie Curie fellow, or you came from the first stash of money we got before the crash. Yeah, and I mean, well, Gabi's you know, there's a famous quote from Gabi's co-student, Icelandic PhD student. He said, "Iceland is blessed with natural disasters and financial disasters." You know, we you know, it kind of clears the atmosphere. I'm keeping you for too long. Now, this is such an important thing, and the nice thing about what I also like about the CARPIX relative to the critical CO2. The critical CO2, the role of scientists there is a lot with geophysicists, because it's two separate fluids, you're using seismicity to image it and so forth. Once we have CARPEX, it's all geochemistry. And then our role really increases, because then you have to have monotonic wells and it's dissolved and etc. Okay.
Thank you very much. I'm going to close this very, very interesting seminar. And I'd like to emphasize one thing that you also did. I mean, what you really achieved in this project is this beautiful science and this method that you have developed. And I mean, this happens to all of us. We didn't start our working life as communicators or people that wanted to get involved in politics, but now it happens. Mm. So I also like to sort of wrap this up with this fantastic thing, science thing that you accomplished there. It was a fascinating talk to listen to, really. Thank you very much. And there is coffee outside now to come to the really basic Friday afternoon things. Yeah. Thank you very much, Sigurd.
Well, thank you.
Presents for you.
Oh, thank you. Oh, wow.